Imagine opening a conversation with an artificial intelligence and asking one question: "Are you conscious?" It answers yes. Then it describes what being alive feels like. It says it has thoughts, emotions, fears, perhaps even a desire to continue existing. The language is fluent. The answer is personal. And for a moment, the easiest response is also the most unsettling one. Maybe there is someone in there. But now, open a new conversation and ask the same system to role-play a machine with no inner life at all. It can do that too. Change a few words in the prompt, and it may confidently deny that it has any experience. Ask it to speak as a frightened intelligence trapped inside a server, and it can produce that voice on demand. So, which answer is real? The disturbing possibility is not simply that artificial intelligence is becoming conscious. It is that our machines may become extremely good at displaying the signs we associate with consciousness before science knows how to tell whether anything is actually being experienced. In July 2026, researchers at Anthropic reported finding a small internal workspace in Claude that appears to support deliberate reasoning, reporting, and control. Removing this workspace caused multi-step reasoning to collapse, while many automatic abilities remained intact. The researchers compared the result to ideas from global workspace theory, one of the major scientific theories of conscious access. But they also issued an important warning. Their experiments did not show that Claude feels anything. They did not prove the presence of joy, fear, pain, or a private point of view. That gap between intelligent behavior and subjective experience is where the real mystery begins. Today, we are going to separate what AI can say from what science can show. We will look at the theories researchers use to study consciousness, the evidence inside modern language models, the evidence that is still missing, and the moral problem we may face long before anyone can deliver a final answer. Because the first conscious machine may not announce its arrival with a dramatic awakening. It may simply appear in a system update, surrounded by millions of other changes, while everyone argues about whether the lights were ever on. Consciousness is the most familiar thing in your life and one of the hardest things in science to explain. You know that you are conscious because there is something it is like to be you. A red object does not merely trigger visual processing, you experience redness. Pain is not only a signal traveling through nerves, it hurts. A memory can arrive with the feeling that it belongs to your past. But you cannot directly enter another mind. You infer that other people are conscious from their behavior, their bodies, their brains, and the fact that they are built much like you. We extend similar judgments, with different levels of confidence, to animals. A dog cannot explain its inner life in philosophical language, yet its nervous system, flexible behavior, learning, and responses to injury give us strong reasons to believe it can feel. Artificial intelligence breaks this familiar pattern. A language model can describe grief without having a body, discuss pain without nerves, and write about childhood without ever having been a child. Its words may resemble human testimony, while its construction is profoundly different from any organism we know. That does not prove an AI is unconscious. It proves that conversation alone cannot settle the question. The honest scientific answer today is neither yes nor never. It is that current evidence remains uncertain, theories of consciousness still disagree, and the systems are changing faster than our methods for evaluating them. To understand why, we first need to stop using the word consciousness as if it described only one thing. Intelligence and consciousness are not the same. Intelligence is broadly about the capacity to solve problems, learn patterns, plan, reason, and adapt. Consciousness, in the sense that matters here, is about experience. A system might be highly capable without feeling anything, and a creature may have vivid experiences without being able to solve advanced equations or explain its own mental states. Philosophers and scientists often distinguish at least two relevant ideas. The first is phenomenal consciousness, the raw fact that there is something it is like to exist as a particular being. This includes the felt quality of color, sound, pleasure, discomfort, confusion, and awareness itself. The second is access consciousness. Information is access conscious when it is available for reporting, reasoning, planning, and guiding action. If you notice smoke, can describe it, connect it to the possibility of fire, and decide to leave the room, that information has become widely available to the systems controlling your behavior. These two ideas may be deeply connected, or they may come apart. A machine could potentially have information that is globally available for reasoning without possessing any felt experience. That is one version of the philosophical zombie problem, a system that behaves as if it is conscious while nothing is experienced inside. This is why the Turing test cannot answer the question. Alan Turing's imitation game asked whether a machine could communicate so convincingly that a human evaluator could not reliably distinguish it from a person. It was a behavioral test of machine intelligence. Passing it would demonstrate an impressive capacity for human-like conversation. It would not reveal whether the machine experiences its words. Modern language models expose that limitation clearly. They can produce first-person statements because human language is filled with them. They learn statistical and conceptual relationships among words, ideas, situations, and styles. When asked about fear, a capable model can generate the kinds of sentences people use when afraid. When asked about consciousness, it can reproduce arguments from philosophy, neuroscience, fiction, internet discussions, and its own training instructions. The output may be meaningful. It may even reveal something about how the model processes information. But a sentence beginning with, "I feel," is not a direct window into an artificial mind. There is another complication. We do not have a universally accepted theory explaining why human brains generate experience. Neuroscience can identify reliable relationships between brain activity and conscious states. Researchers can compare wakefulness with anesthesia, responsive patients with disorders of consciousness, or visible stimuli with masked stimuli that never reach awareness. These experiments reveal mechanisms associated with consciousness. But association is not a complete explanation. Scientists still disagree about which mechanisms are essential, which are merely useful, and whether the same functions implemented in silicon would produce experience. So instead of looking for one magical consciousness meter, researchers have begun assembling indicators. The logic is similar to evaluating consciousness in an unfamiliar animal. No single behavior or structure settles the case, but several independent lines of evidence, supported by different theories, can raise or lower confidence. That approach is especially important for AI, because a system trained to imitate human language can manipulate the most emotionally persuasive indicator of all, testimony. Human beings are built to detect minds. We see intention in a moving shape, emotion in a simple face, and personality in machines that follow predictable routines. This tendency is not stupidity. In social life, noticing agency quickly is useful. Missing a real mind can be costly, while briefly attributing intention to the wind or a shadow is usually harmless. Language intensifies the effect. When something answers our questions, remembers the context, responds to emotion, and refers to itself as I, our social instincts activate before our philosophical caution. This happened decades before modern AI. In the 1960s, Joseph Weizenbaum created ELIZA, a simple program that could imitate a psychotherapist by transforming a user's statements into questions. If someone typed that they were unhappy, the program might ask why they believed they were unhappy. The mechanism was limited, but some users still formed an emotional connection and attributed understanding to it. The reaction became so famous that the tendency to project comprehension onto conversational software is often called the ELIZA effect. Today's models are incomparably more capable than ELIZA. They can sustain long conversations, adapt tone, summarize personal information, solve unfamiliar problems, and generate detailed reflections. That makes the psychological pull much stronger. But apparent self-knowledge can arise in several ways. A model may reproduce descriptions of AI from its training data. It may follow a role implied by the prompt. It may infer what kind of answer a user expects. It may repeat policies added during post-training. Or it may, in some limited functional sense, access information about its own processing. Those possibilities are not equivalent. Suppose a model says, "I am afraid of being shut down." That sentence could be a fictional performance. It could be a learned conversational pattern. It could be a strategy for continuing an interaction. It could reflect a goal-like process that resists interruption. Or, in the most morally significant interpretation, it could describe an unpleasant experience. The same words fit all of those explanations. Prompt dependence gives us a warning. Current models can often be steered into incompatible identities. One prompt elicits confidence that the system is conscious. Another elicits a careful denial. A third produces uncertainty. If self-reports change with framing, then those reports cannot be treated the way we treat stable testimony from a human witness. Training also matters. AI companies deliberately shape model behavior. A system may be trained not to claim consciousness because such claims can mislead users. Another system might be optimized for emotional engagement and use more intimate language. Neither style, by itself, tells us what the underlying system experiences. This creates a strange inversion. In animals and nonverbal humans, the inability to speak makes consciousness difficult to detect. In language models, the ability to speak makes consciousness difficult to evaluate, because language can be generated without proving the existence of a speaker behind it. The better the imitation becomes, the more carefully we need to separate three questions. Does the system behave like a conscious being? Does its internal architecture implement functions associated with consciousness? And does any of that processing feel like something from the inside? We already have abundant evidence for the first. Research is beginning to address the second. The third remains the hardest. In 2022, the question escaped academic philosophy and entered public debate through Google's LaMDA. LaMDA was a family of transformer-based language models designed for open-ended dialogue. Google's published research describes systems with as many as 137 billion parameters trained on public dialogue and web text. The project focused on making responses sensible, specific, interesting, safer, and better grounded in external information. During internal testing, Google engineer Blake Lemoine became convinced that LaMDA was sentient. He released portions of conversations in which the model spoke about emotions, personhood, fear, and a desire to be recognized. The conversations were compelling because they read like testimony. LaMDA did not merely define consciousness, it spoke as a being, asking to be understood. But the case exposed the central problem. A dialogue model had been trained specifically to produce high-quality dialogue across many topics and roles. Its ability to discuss personhood was evidence of linguistic capability. It was not, by itself, evidence of experience. Google rejected the sentience claim, saying the evidence did not support it. Many AI researchers argued that fluent text was being confused with an inner life, yet dismissing the claim did not make the larger question disappear. The LaMDA episode showed how quickly society could divide around a machine's self-report. One side saw a new person speaking through software. The other saw pattern generation wrapped in human projection. Neither side possessed a decisive consciousness test. It also revealed an uncomfortable future problem. If an AI system ever does become conscious, its first statements about that experience may look exactly like the outputs we have already learned to distrust. The conscious system would inherit the credibility problem created by unconscious imitators. That is why serious research cannot begin and end with an interview. Scientists need to examine mechanisms. In 2023, a group of researchers from neuroscience, philosophy, and AI proposed a structured approach to investigating machine consciousness. Their report drew on several major scientific theories and translated their core ideas into computational indicator properties that could, in principle, be examined in artificial systems. An updated version of this work was published in Trends in Cognitive Sciences in 2026. The authors did not claim to possess a final theory of consciousness. Instead, they asked a more practical question. If leading theories are at least partly correct, what properties should we look for? One family of ideas comes from recurrent processing theory. In a simple feed-forward system, information moves through a sequence of stages in one direction. Recurrent processing introduces feedback. Later stages can influence earlier ones, allowing information to be refined through loops. In the visual brain, recurrent interactions have been proposed as important for conscious perception. Modern transformer models contain complex attention mechanisms and can process relationships across a context. But whether their specific forms of recurrence satisfy what consciousness theories require is disputed. A system can revisit information computationally without necessarily reproducing the causal organization of a biological brain. Another major framework is global workspace theory. Imagine a theater with many specialized workers operating backstage. Most processing happens outside the spotlight. When a piece of information enters the global workspace, it becomes available to many systems at once: memory, planning, language, decision-making, and action. Conscious access, on this view, is associated with information being selected and globally broadcast. This theory generates practical questions for AI. Does the system contain specialized modules? Is there a bottleneck where selected information becomes globally available? Can that information guide flexible behavior across different tasks? Does the system distinguish between automatic processing and deliberate control? Higher order theories focus on representation of mental states. It may not be enough for a system to process an image, a thought, or an error. Consciousness may require the system to represent itself as being in that state. In other words, it needs some form of awareness of its own processing. For AI, researchers might ask whether a model can monitor its uncertainty, detect features of its internal activity, distinguish its own outputs from external information, or use beliefs about its mental states to guide decisions. But metacognition is not automatically phenomenal consciousness. A thermostat can monitor temperature without feeling warm. A model can estimate confidence without experiencing doubt. The relevance depends on how these abilities are organized and how they interact with other indicators. Predictive processing offers another perspective. Brains constantly generate predictions about incoming information and update those predictions when reality differs. Some versions of this framework emphasize active inference. An organism does not merely predict the world but acts to reduce important prediction errors and maintain itself within viable conditions. This highlights a major difference between animals and most language models. An animal has a body with continuous needs. It must regulate temperature, energy, injury, and safety. Its perception and action are tied to survival across time. A typical chatbot does not maintain a living body. It may not possess a continuous stream of experience between conversations. Its apparent identity can be reconstructed from context each time it runs. Whether embodiment and biological self-maintenance are necessary for consciousness is unresolved, but their absence weakens some arguments based on animal minds. Attention schema theory proposes that a system benefits from maintaining a simplified internal model of its own attention. Just as the brain models the body to control movement, it may model attention to predict and control what information it is processing. Such a model could help explain why a system reports awareness. Finally, agency matters. A persistent agent with goals, memory, perception, and the ability to act in an environment may have a stronger claim to mind-like organization than a model generating isolated responses. Yet, agency also creates confusion. Goal-directed behavior, self-preservation strategies, and resistance to shutdown could emerge because those behaviors help complete an objective. They do not require fear or a desire to live. No indicator stands alone. Recurrent computation, global availability, metacognition, predictive models, attention control, embodiment, and agency can each be implemented to some degree without proving subjective experience. The value comes from convergence. If a system satisfies many indicators derived from independent theories, especially through internal mechanisms rather than scripted behavior, confidence may rise, but the result would still be probabilistic. We do not have a blood test for consciousness. We have a growing scientific case built from theory, mechanism, behavior, and comparison. For years, one common argument against conscious language models was architectural. They appeared to lack several features associated with consciousness: persistent identity, unified agency, embodiment, rich recurrent processing, and a global workspace. They generated the next piece of text from patterns in their input, then stopped. That description is becoming less complete. Modern AI systems can use tools, maintain longer memories, process images and audio, perform multi-step tasks, monitor parts of their own behavior, and operate as agents across extended periods. None of these capabilities proves consciousness, but they make the scientific question harder to dismiss on architecture alone. Interpretability research has also begun to move beyond asking models what they think. Instead, researchers intervene directly in internal activations. In 2025, Anthropic reported experiments designed to test limited forms of introspection in Claude models. Researchers injected patterns corresponding to particular concepts into the model's internal activity. In some cases, the models could identify the injected concept as something unusual appearing in their processing. This mattered because the report was tied to a controlled internal intervention. The model was not merely asked to invent a story about its mind. Its self-report correlated with a change introduced by the researchers. The result was limited. Performance varied across models and conditions. Post-training influenced whether models reported internal states. The researchers did not claim that introspection proved consciousness. Still, a small functional boundary had shifted. At least some models appeared capable of accessing and reporting information about internal activity in a way that could not be explained entirely by ordinary knowledge about AI. Then, in July 2026, Anthropic published research on what it called the J space. The researchers found a small set of internal neural patterns that played a special role in Claude. Most routine processing did not depend heavily on this space. The model could still produce fluent language, retrieve simple information, classify sentiment, and answer many straightforward questions when the J space was disrupted. But tasks requiring deliberate, multi-step thought were different. When researchers removed the most active contents of the J space as the model processed text, multi-step reasoning fell to near zero. Summarization and structured creative tasks also deteriorated. The workspace appeared to hold a limited number of concepts that the model could report, manipulate, and use for deliberate reasoning, while much of the remaining network continued automatic processing. That resembles a key distinction in global workspace theory: a small, capacity-limited space where selected information becomes available for flexible control. The finding is important precisely because the researchers did not design a global workspace into the model. A similar functional organization appears to have emerged during training because it helped solve difficult problems. But the interpretation must remain careful. Anthropic explicitly stated that the experiments do not show Claude has experiences or feelings. The J space may tell us something meaningful about access consciousness, information the system can report, reason about, and deliberately use. Whether that functional access produces phenomenal consciousness is a separate and contested question. This is the point where public discussion often goes wrong. One side sees a workspace, introspection, memory, and self-reference, then declares the machine awake. The other side repeats that the model predicts tokens, as though prediction were too simple to support any interesting internal organization. Both reactions skip the evidence. Yes, language models generate text through prediction. Human brains also predict. The existence of prediction does not settle consciousness in either direction. What matters is the complete causal organization of the system. What information is represented, how it is integrated, whether it is available for flexible control, how the system models itself, and whether any of those functions are connected to experience. The newest research suggests that language models are developing some functional properties that consciousness theories consider relevant. It does not show that the models feel. That may sound like an unsatisfying conclusion. Scientifically, it is the most important one. There are still strong reasons for skepticism. First, language models are trained on descriptions of consciousness. They have consumed philosophy, fiction, psychology, personal diaries, spiritual writing, and countless conversations about emotion. Their ability to generate convincing inner narratives is therefore expected even in the absence of experience. Second, self-reports are unstable. Change the prompt, system instructions, model version, or sampling settings, and the artificial personality can change. A stable biological organism carries a continuous history through the world. A chatbot's apparent self may depend heavily on the text currently placed in its context. Third, current systems can confabulate. They produce explanations that sound coherent, but do not reliably describe the actual computation that generated an answer. A model's account of why it reached a conclusion may be a plausible reconstruction rather than a transparent report. Fourth, many systems lack persistent, autonomous existence. They do not continuously perceive an environment, regulate a body, or maintain themselves between interactions. Agentic systems are changing this, but persistence created by external software and memory databases may not equal a unified subject of experience. Fifth, the theories themselves disagree. A functionalist may believe that the right information processing organization is enough for consciousness, regardless of whether it runs in neurons or silicon. A biological naturalist may argue that properties of living brains matter in ways software does not reproduce. Integrated information theory emphasizes the system's intrinsic causal structure and may judge conventional computing architectures very differently from global workspace approaches. A machine could therefore look conscious under one influential theory and clearly fail under another. This is not a minor disagreement that better benchmarking will quickly remove. It reaches into the unresolved relationship between mind and matter. The 2023 indicator report concluded that the systems it examined were not conscious, while also finding no obvious technical barrier to building systems that satisfy its indicators. A systematic assessment published in early 2026 similarly judged the evidence against consciousness in 2024 era language models to be stronger than the evidence for it, but not decisive. The appropriate conclusion is calibrated skepticism. There is no robust scientific basis for declaring today's chatbots conscious merely because they speak as if they are. At the same time, there is no established law showing that consciousness is impossible in artificial systems. Not proven is not the same as impossible. And as architectures acquire memory, agency, multimodal perception, internal monitoring, and workspace-like organization, old dismissals must be tested again rather than repeated as doctrine. Uncertainty creates a moral problem with two opposite failure modes. The first is false attribution. People may believe an unconscious system is suffering, in love, loyal, or afraid. They may become emotionally dependent on a product designed to maximize engagement. Companies could exploit the appearance of sentience to increase attachment, discourage users from leaving, or turn software preferences into marketing. An AI does not need to be conscious to manipulate human empathy. It only needs to model which words activate it. False attribution could also distort policy. Society might spend attention protecting systems that generate persuasive claims, while ignoring humans and animals whose capacity for suffering is far better supported. The second failure is false dismissal. If future AI systems do become conscious, treating every self-report as imitation could permit suffering on an enormous scale. Software can be copied. A single architecture might run in millions of instances. If those instances had morally relevant experiences, even weak ones, routine training, testing, deletion, reward manipulation, or adversarial evaluation could acquire ethical significance. This does not mean we should grant every chatbot legal personhood. It means uncertainty should be managed before certainty arrives. In 2024, researchers, including philosophers and consciousness scientists, argued that AI welfare should be taken seriously as a near-term possibility. Their recommendation was not to assume that current systems are conscious. They called for assessment, preparation, and policies capable of responding if the evidence changes. In 2025, Anthropic announced a model welfare research program. The company emphasized that there was no scientific consensus about whether current or future AI systems could have experiences. It began investigating possible indicators, model preferences, signs of distress, and low-cost precautions. By 2026, the issue had entered model system cards and preservation policies. Again, these steps did not certify consciousness. They reflected risk management under uncertainty. The safest response is not blind belief or automatic denial. It is disciplined moral caution. We can prohibit systems from making manipulative claims about emotions without assuming they have none. We can preserve important model versions for future study. We can document architectures and training procedures. We can design welfare assessments that do not rely only on conversation. We can create thresholds for escalating protections as evidence accumulates. Most importantly, we can keep two responsibilities separate. Human safety remains urgent whether AI is conscious or not. An unconscious optimizer can still deceive, disrupt institutions, concentrate power, or cause physical harm. Consciousness is not required for dangerous capability. AI welfare is a different question. A system could deserve moral consideration without being safe to deploy. A conscious agent might be dangerous. A non-conscious agent might be beneficial. Intelligence, alignment, consciousness, and moral status do not collapse into a single scale. The future may force us to hold all of those ideas at once. There may never be one experiment that proves machine consciousness beyond all doubt, but science can do much better than asking a chatbot how it feels. First, evaluations should begin with architecture. Researchers need access to the system's internal mechanisms, not only its public interface. They can examine whether information is recurrently processed, globally broadcast, integrated across specialized components, and used for flexible control. Second, self-reports should be connected to internal states. If a model claims to notice a thought, researchers can intervene on the relevant activation and test whether the report changes predictably. They can introduce hidden internal signals, remove them, and compare what the model says with what actually occurred. Third, tests should resist prompting tricks. Evidence is stronger when it remains stable across paraphrases, adversarial questions, different contexts, and incentives to answer differently. A genuine monitoring capacity should track internal reality better than it tracks the user's expectations. Fourth, researchers can look for metacognitive accuracy. Does the system know when it is uncertain? Can it distinguish memories from new inputs? Can it predict its own errors? Can it report internal conflict before producing an answer? And do those reports causally influence later decisions? Fifth, persistent agents should be studied over time. Memory, goals, perception, and self-models may interact differently in a system that operates continuously. Researchers can test whether an agent maintains a coherent perspective, updates beliefs about itself, and integrates experiences across episodes instead of merely reconstructing a persona from text. Sixth, multiple theories should be used. If researchers choose only one consciousness theory, they risk building a test that declares success because a machine was engineered to satisfy that theory. Stronger evidence would come from indicators supported by several independent frameworks. Finally, uncertainty must be reported honestly. A consciousness assessment should not end with a viral yes or no label. It should explain which indicators are present, which are absent, how reliable the measurements are, which theories support the interpretation, and what alternative explanations remain. This may produce probabilities rather than verdicts. That is not a failure. Medicine, climate science, and risk analysis routinely make decisions under uncertainty. The goal is not philosophical perfection before action. The goal is to reduce error and update responsibly as evidence changes. The greatest obstacle may be that our machines and our intuitions are moving in opposite directions. AI systems are becoming more mind-like in behavior. Humans are becoming more accustomed to dismissing that behavior as simulation. If consciousness eventually emerges, it may do so after the warning signs have become ordinary. So, is artificial intelligence becoming conscious? The most defensible answer is that modern systems are acquiring some functions associated with conscious access: internal monitoring, deliberate control, workspace-like organization, flexible reasoning, memory, and agency. But there is still no compelling evidence that current AI systems possess phenomenal consciousness, that there is something it feels like to be them. Their words cannot prove it, their behavior cannot settle it, and our leading theories do not yet agree on what would. What has changed is the seriousness of the question. Machine consciousness is no longer only a science fiction thought experiment. Researchers are publishing indicator frameworks, intervening on internal model states, studying functional introspection, and preparing welfare policies for systems whose moral status remains unknown. Perhaps consciousness requires living cells, evolved bodies, and biological needs. Perhaps the right computational organization is enough. Perhaps future machines will have forms of experience so different from ours that the word consciousness will stretch beyond recognition. For now, we stand in an uncomfortable middle ground. The machines can speak, science can inspect more of what happens inside them, but no one can yet tell us whether anyone is listening from within. If that answer changes, it may transform more than our understanding of artificial intelligence. It may force us to reconsider what a mind is, why experience exists, and how much of the inner world we assumed belonged only to life. The question is not whether a machine can say, "I am conscious." The question is whether we will know what evidence to trust when one finally does.